try again. Yeah, you can. You are able. Yeah, yeah, you're good. Okay. So I'm waiting for at least to be 100, 110 out of the 140 students, so we can start. Usually, you guys walk into the classroom late with lunch and things like that. So I wait a few minutes.
You gotta give extra credit to the ones who are here, Professor.
Everybody's at home? Probably yes.
I think his mic is still on. There's just a lot of background noise.
So how are we doing so far? The class looks reasonable. Can you follow the material?
Yes.
If somebody's awake, you can answer. Okay, thanks. I'm trying to make it more attractive. I mean, you can listen to the lecture. You can. It's recorded by Liba, so we have to thank her for that. And then I also post kind of a summary of the lecture, and there's also a book which probably has the same stuff, but it has more material. So you should be okay. If anybody is really interested in learning, I think you can easily do that.
Professor, when is the first midterm?
I told you that, we asked that question before, and let me I just want to look at the chat for a moment. Okay, so what I mentioned to that question before is that probably we have to wait a little bit until we accumulate enough material, and then we can do maybe a first midterm, and we're going to vote on that. We're going to vote on the dates. If you want, we can start thinking about it next Thursday. So I'll try to bring up a calendar, and we'll see what is the most vote. You know what, let me just try. How can you vote? You can do a hands up, or
you can do a poll, Professor, on the thing on Zoom.
Is it just gonna be based off of the lecture and the homeworks?
Yeah. If you wish, I can ask you topics from other courses and from maybe different ones, but you don't want to.
Yeah, I was thinking maybe we just throw some thermodynamics in there. Why not, Professor?
Yeah, and if you follow me, I kind of usually tell you what I expect you to be able to solve. So I keep on repeating it, and just pay attention to what I'm saying usually. So how about we start? I mean, we waited now for the students. We have 110 out of 140. I'll catch those later on, those that don't show up. Okay, so we start. Okay, let me do a share. Okay, I'll do this one. Okay, you want full screen? Yes, I hear a voice. Yes or no?
Yes, please.
Yes, please. Full screen would be preferred.
Full screen it is. Full screen gives me the pen. Okay, so I usually do a really short summary of what we did before, and we looked at the solid body acceleration of fluid particles. What we mean by that is that all the fluid particles accelerate at once, and then there is no relative motion. So the two cases that looks reasonable for that type of assumption was a container was kind of rectangular, accelerating to one direction, and then the surface kind of aligned in a straight line according to the acceleration. We answered question about what is the pressure inside the liquid and what is the shape of the surface. It turned out to be a straight line. And then we also showed that you can actually skip all that and just look at the depth at that point and use the old formula rho GH. Then we did the other case of acceleration, which is rotation, when here we have centrifugal or radial acceleration, that's the proper term. And we solved that case, and we've seen that the pressure everywhere is described by this formula here. Right here, that's the formula, we developed that. And then we try to see what is the shape of the upper surface. And hey, we got that one. Turns out this is a parabola. And actually the difference is between the lower point and the higher point, between these two. That distance is this term. Okay. And 1/2 of it is going to be the middle line, which turns out to be the initial level of the fluid, or the final level of the fluid once the container stops spinning. Okay, so that's just a brief summary. Here is exactly what it is. So we can take the average, look at the average height of the container when it's not spinning, and then the minimum is going to be minus that quantity, which is, remember, it's divided by 4, which is 1/2 of the 2g we had before. And the same distance up in order to get the maximum height. And then again, here I mentioned that we can use the good formula that the pressure is actually changing by the depth rho g. So it's the same condition. Okay, so that was done last time. And then I started the more important part of that particular chapter, which is the forces due to the pressure variation. So we looked at a pool of water, and there's a depth h like before, nothing new. There is an object. What happens? Somebody stepped on your toes. Somebody was anyway, and there's an object here. Let me get the pen. There's an object down here, this one. And then the question is, what is the force on that one and what is the direction? So naturally, we said that the delta F is equal to the pressure, or delta P, what is there, the pressure over there, multiplied by the area. That would be the direction which is normal to the surface. And if you want to have a vector form, then if you know what is the unit vector, and then we want it to the x direction, then we have to take the cosine of that, which is simply that product, the scalar multiplication, which is right here. Instead of doing complicated shapes and really complicated normal, then what can happen is this normal can vary with the shape of the object, and the integration becomes pretty complicated. So we try to avoid that, because the message is how to get the forces and how to calculate the pressure, the center of pressure, which is the important part. So we decided just let's go with a straight surface. Okay, and for that purpose, we ended up with a very simple model. So this is our simple model. And we said, okay, here's a container, pool you may call it, and it's filled with liquid. Can say water, it's a pool in the backyard. And there is a plate here, surface, which is a solid surface here. And it's planar, it's flat. Okay, it's flat. And then somewhere here, there's going to be an area.
Nesse peso que eu estou hoje, né? Eu, de um tempo para cá, eu venho engordando e não tenho mais essa facilidade de perder esse peso, né? E também por conta da flacidez.
Is it a question, or I don't know? I didn't hear you very well. It's a question, or you're just talking to?
No, Professor, it's not a question. There's someone not muted.
Or someone is just talking to her neighbor. Okay, so I continue. So we have a container, we have a flat surface. This is a simplification instead of having some curly shape. And then there's an area that, as an engineer, you want to know what is the force on that one. It could be a window, could be a valve, could be a reinforcement, whatever, door. And that's the engineering. Okay. Bless you. I think somebody had, okay, anyway. So what are the questions? What is the force? And where is the center of pressure? Now, if I look at the pressure distribution here, it's going to be linear. So the lower portion gets larger pressure than the front. So suppose everything is symmetric and this is the center, I would still think that the resultant force will act below that geometrical center. That just looks logical, which will turn out to be true. So we took the same equation as before, and we added the pressure outside because that's the total pressure, but also on the other side of the plate, there's PA. So we decided, let's forget about it, cross it out. Then we're trying to develop the formulation for that model. Now note that we place the coordinate system at the intersection between the liquid surface and then the plate, the top of the plate. That's how we place that. Therefore, it's worth looking into the relation between the depth of a certain point versus the y coordinate along to the coordinate system we picked up for this case. Again, I followed most of the books, and most of the books will have the x, y coordinate like that, and then of course this will be the y, and then the x is going to point into the board.
Professor, why did we cancel PA? Is it because that's just the ambient pressure? It's acting on both sides?
The ambient pressure is PA. So if you really want to have the absolute pressure at that point, you have to use PA. PA is going to be a constant working. So the PA is simply going to be, the force due to PA, simply going to be PA times the area, because PA is a constant contribution to that quantity. However, on the other side, we also have PA acting on the same surface.
Got it. So it just cancels. Okay, I see.
Yeah, we cancel it out.
Got it. Thank you.
This is gauge pressure versus differential pressure. People use that. Anyway, so see if I touch, I keep on complaining that I touch the mouse, this thing jumps. So bottom line, I just want to emphasize how we developed the model. And then simply the force. The force is going to be rho g sine alpha, which is rho gh basically, and y ds. So we have to integrate each y, what is the pressure. So if this is, let's say this is the segment, then here the pressure is this much, here the pressure is this much. I'm just sketching something here. So these are segments of delta y, dy, times the pressure, that's the force. So this is what it is. So y and ds is going to be delta y and delta x. It depends on the width or the size of this component. Okay, so this is very straightforward. So we develop, that's fine. And that we can really simplify the problem. So how, and I don't want to repeat the formulas, but here's the result. And the result's actually going to help us solve problems very easily. Now, I mentioned again to the question you started earlier, what you need to know for exams and homework. And yeah, I developed the formulation, but at the end of the day, this picture summarizes that particular topic. And I expect you to be able to use that page and solve problems, which we're going to do in a minute with the examples. Okay, so what happened? Here's the model again. And then I show the view from below. Then you see the x coordinate as well. Here is some shape, which you can, okay, I touched the mouse, so yeah, okay. I have to pay for that. Let me get the pen. Okay, so here is the surface that we're interested in. Sorry, this one is here, and this one is here. And the surface we're interested in here is that. So imagine that this is the shape of the surface, and this is at the back of that pool. Okay, so now here's the process. So we did the integrals and all that, but now we want to make it simple. So step one, find the centroid of the area. Okay, step one. Then you can go either find a moment of inertia, but then the next question is, what is the depth at that particular point? So you can use that formula. So sometimes the depth is given, sometimes the length is given, sometimes the length is not given. Then you have to create a coordinate system which will follow exactly this model. Many of the tricks that we play with the exams and with the homework are about this, how to place the coordinate system. So if you find the depth of that centroid, so this is the centroid of the area, which is a reflection of that point. I'm not super accurate. Here, that one. You have to find out what is the depth, which is this one. This is the depth of that point, which is going to be H average now. So therefore, you found the average depth, and therefore the pressure, very simply, just rho GH. Okay, same formula. What is the force? The force Fz, which is going to be minus, so this is Fz, the Z direction, and the force is going to act this way, which is the minus. It's going to be acting simply the average pressure times the area, very simple. You can look at the shape of the pressure distribution, which is kind of linear. So it's very simple to assume that here's a maximum here, here's minimum this side, and take the average, this plus that one times 2, or divided by 2, and that's the average pressure. Okay, now next, the next question is, where is the center of pressure? So in this particular case, I would guess that the center of pressure will be below, but it looks like there's more area here, so I would bet that the center of pressure is somewhere here on the side, on this particular case. So in order to answer that question, you have to find out what is the moment of inertia. Now we again simplify. The moment of inertia is going to be about these two axes which cross the centroid. So this would be XX, and this is going to be XY. Okay, and so XCP minus X average. Okay, so the shift left or right is going to be the combined moment of inertia. Okay, and that's this one. And the shift down of the center of pressure is going to be that. Now, one more time, moment of inertia. You have a wheel. You have your bicycle wheel, and then you spin it around this axis. Okay, and let's say this is the x-axis. Okay, and this is the y-axis. So if everything is completely balanced, then you're going to have moments of inertia about the x-axis. But if you add a little weight here, then it's going to create forces to other direction. If it's spinning, it's going to go also to the y and z direction. Therefore, there's going to be a mixed moment of inertia, which is represented by that. Okay, so it's very much the same as in dynamics. Anyway, this is what you need to remember, and let us do some examples, and you're going to see it's very, very simple. So where can I play tricks on you? I can play tricks with the coordinate system, maybe with the moments of inertia. That's where we can place. Okay, so
Professor?
hopefully, yes.
What does the S stand for?
Which one?
S? The letter, yeah, the letter S, yes.
The capital S represents the area. Okay, one more time. Capital S represents the area of the area of the section we are interested in finding out the force.
Okay, thank you.
Okay. All right, let's go do some examples, and then everything is going to be clarified. Oh, I placed here this table showing typical shapes. We're going to use rectangle for sure, circle for sure, and triangles. Probably not going to use the others. Probably the others that just to calculate the moment of inertia, it's going to be complicated. And again, this is not a static course, so this guy is already pretty complicated. This is, you can do that, but I don't want you to start spending half an hour figuring out what's the moment of inertia. So the most complicated case we're going to be this, and I'm going to do an example on that today. Okay, so this is the most complexity we're going to have. Okay, let's do the most the simplest case, Okay, so let's see. So, okay. So we have a gate, okay, a gate here, appears to be symmetric, okay? And then it is blocked here. So this part belongs to the gate. That doesn't matter, okay. It's 2 meters wide, 4 meters high, located in that direction. So it shows that it's 10 meters below. So I can just, by looking at that, I see the centroid is actually at 12 meters. I can just look at that right away. So we don't have to be a genius to figure that one out. So the centroid is at 12. A centroid of a rectangle is right here in the middle. Also, it is symmetric. This way, it is symmetric left and right. So I would think that IXY is going to be equal 0. Okay. I would expect you to figure those things out almost immediately. It's not rocket science. It's coming from dynamics, statics, the same way. Okay. So this is what we have. And so I'm just, so we need to calculate the force on that and then calculate the center of pressure. And what is the magnitude of the, okay, calculate the center of pressure. What is the, oh, that's it, that's all. Sometimes we're gonna ask if, let's say this little portion is pulling the, or holding the gate in place, what would be the force that is trying to open it up? In the next other questions we're going to ask you. So that could be a very, very simple, because then you have to do the moments. Okay, let's do what's at hand. So if we go follow the previous sequence, find out where is the average depth. But turns out that the coordinate system is like that. This is Y, and this is, sorry, this is Y, and this is Z. And turns out that Y average actually is equal to H average. It's the same thing, it's just going straight because sine alpha is 0. Okay, so we just, by looking at that, by just looking at the dimension, we find out that the centroid of this particular gate is at the depth of 12 meters, which is 10 plus the center of the 4. The area of that plate, very simple, 2 by 4, 8 meters squared. What is the average pressure at the centroid? Well, it's 12 meters deep. Okay, so we have 1,000 is the density of the water, G is gravitation, 12 meter depth. If my calculator is correct, then I end up with this number, which is the pressure down there. Okay, how much is the force? Simply take the average pressure at the centroid, multiply by the area. Remember S, that's the question you asked before. S is the area of the gate. Multiplied by 8, I end up with some big number. So let me just speculate. If I cut it here, then it's probably kilogram force. I divide it by, it's like 94 tons, metric tons. That's pretty serious force, pretty serious force. How much is the center of pressure shifted, and where it is shifted? It's shifted down for sure, because the pressure distribution looks like this, right? This is the pressure distribution, and it's more pressure on the lower part than on the upper part. So clearly the resultant force is going to act below. So IXX, here's the IXX. B is the width, L is the height. So B, height to the third, divided by 12. That's from the table, okay, from the table, or this 12, whatever. Yeah, this is, I think this is the moment of inertia. This other 12 is the average Y, which we calculated here. And remember, that's the average Y, that's not the depth. But in this particular case, they are identical. And the area of the gate is this. Do the algebra, 0.1, so 11 centimeters. So if this is 2 meters, this is 1 meter, so it's somewhere here.
Professor,
Yes, sir.
how do we find P, or are we supposed to know that?
The
Like
pressure,
P bar?
P average, this guy
Yes.
right here.
So we know the density and the gravity already.
Density, it's water. Where is that?
Or do we
Water.
do, we do the
Water.
default?
Water. Okay, we have water. Density
Okay.
of water is 1,000. You should know that if you take shower every day. Okay?
All right.
All right. No, I'm joking. You know, so we have to make it easy. So that's water. You should know that. Okay.
What's-
I assume,
Professor,
Yeah, go ahead.
the density of water is 1,000. What's the units?
Kilograms per meter cubed, right?
Okay, it's kilogram
It's kilogram. It's grams per centimeters cubed, I think.
meter cube. We had at the beginning of the first class, I mentioned that we're going to use metric units. I don't know how difficult it is to sell that to you guys, but even the British are using metric, okay? Even you go to England, everything is metric. The only thing which is not is miles per hour on the road, but they're trying to do that, even that, trying to fix that. But if you go engineering in England, everything is metric. So I think we are the last place here that some people use the SAE unit. This is a correct question, but I expect you guys to know these things. And by the way, the kilogram was defined based on water, on 1 liter of water, which is 1,000, which is 10 centimeter by 10 centimeter. Okay, like 10 centimeter, 10 centimeter, 10 centimeter, which is called in decimeter. And the French are responsible for that, okay? So don't blame me. Anyway, so you know what? Let me do that again. Let me go here. So the process, find the centroid. You with me? The person that asked the question.
Yes, thank you.
Oh, no, probably there are others who are kind of napping. I just want to repeat it because we're going to continue and just want to repeat. Find the centroid of the area. Things are going to get simple. We're going to have rectangles, I don't know, circles, and perhaps triangles, nothing more difficult. Find the center of the area, which is a centroid, and find how deep that point is. At that point, this is the H, which is the average depth. And you can either you also have to find the average Y based on that formula because they are related. Here you have Y average and not H average. Then find what is the pressure at that point. And from here, it's smooth sailing because the force is going to be this average pressure times the area, okay? And then the shift in the center of pressure, either to the X and Y directions are given by these. So you have to look up the moments of inertia. If the body is symmetric, the X shift, the IXY is going to be 0. Again, statics, dynamics, I'm counting on you that you did that before. Let's do another one. Let's do it more complicated. This looks much more than the example I did before. Okay, so here, see, I have something right in front of me here. Okay, well, all right, so this is exactly the same thing. So we have a 4-meter diameter circular valve, and it has this axis, rotating axis here. So it rotates about this, okay? Rotates about this axis. And this is kind of it. I'm looking at it at the bottom, but this is the valve itself. This is the valve, okay? And the angle is 60 degrees, so it is following pretty much what we have. And it's given that actually the depth H average is 10 meters. So this is basically H average, okay? And 60 degrees and find the force and how much is, where is the center of pressure and what it takes to open it. Why it takes force to open it? Because the center of pressure is somewhere here, and then the force is acting Fz. This is going to be Fz, Fz. And now we have here this little thing, okay? So we would like to push back somehow, either moment or force. If you need to have a moment, for example, we have a moment like that, we need to overcome that moment, which is Fz times this distance. Okay, this is again statics. All those that get A in statics should understand what I just said. Anybody to approve? A in static. Who got A in static? A in static, calling once.
Got a B plus.
I got to be +2. Is that okay?
That's fine. Okay, so you understand what I'm just saying? How much is the moment to open? So it is not going to push on that little piece which is stopping the valve. This is stopper.
That makes
Okay?
sense. Yeah.
Clear?
Yeah, clear.
Okay. All right. So that's the question. So we're trying to mix, mechanics and track. All right. So let's follow the same procedure. So we can actually answer the question about the force almost immediately because we know how deep is the centroid. For a circle, the centroid, this is the centroid. Oh, I touched the screen again. It's going to go away. Okay, I keep on making mistakes. I need to catch the pen first. Okay. So we know this is the centroid. This is a circle. Centroid is the center, no rocket science. How deep it is? 10 meters. So what is the average? What is the pressure at that average point? Rho GH. Again, density of water 1,000. Gravity 9.8 meters second square. And then the depth is 10 meters. And here's some number which is Newton per meter square. Okay. Right? Okay. We got that. What is the area? What is the area of that valve? So it's pi r square. R is 2, so it's going to be pi and 2 square, okay? And this comes out 12.56. Okay, so now we know what is the area and what is the average force. Therefore, the force is going to be minus, of course, because it pushes this direction, minus x direction. This is Fx. This is the magnitude. Of course, I didn't put it in the right place. And so what is the force? Pressure, this is that number. Okay, where's the pressure? Here's the number, 9.8 10 to the 4th. Area, and we get minus 1.2 10 to the 6th Newton. Okay, of course, the minus, why is the minus? Because it is acting opposite to the Z direction, which is positive acting into the pool. That's how we figure that one out. This is a symmetric geometry, the valve. Therefore, XCP is going to be equal to X average. There's not going to be any shift. Okay. Then we're looking at the IXX, the moment of inertia for a circle or circular shape. And it is, says pi r to the 4th over 4. Oh, yeah, I did that the same way. Okay, no problem. So I did it the same way. And then, so we have pi r square. Pi is pi, r square is going to be 2, right? And then 4 is 4. So, yeah, here it is right here. That's what I did, pi r square. That's the area, and pi r square 1/2. I'm just trying to make sure I didn't make any. Y average is going to be 10, which is H sine, okay, H average sine 60. Okay, so it turns out to be 10. But we divided that because we want to know what is the Y average. So it's going to be more than 10. Okay, so that is this one, Y average. And I believe this 4 relates to this 4 here. And everything else is the same. You plug in the numbers, ends up 0.0866. So it's like 8.7 centimeters. 8.7 centimeters. 8.7 centimeters. This much. From here to here, that much. And so the force clearly acts here. So this is incorrect. The FZ acts here, which is 8.7 below. How much is the moment to open the gate? So the moment, as I mentioned, is going to be the distance, this distance times the force Fz, okay? Because we try to overcome that force. So the moment, either we apply the same force here or we apply a moment at a larger distance, okay? And the moment is going to be Fz, and then this distance. So you take 1.23, which is that number here, which is the force, times the 8.7 centimeters, this one. And this is the moment required to open the valve. Okay. Any questions? This is exactly the way we develop the formulation. Yeah.
Professor, is the Y bar same as Y on the drawings?
Is the Y average equal the same as H average? That's the question?
No, same as Y on the drawing?
Y, this is Y, okay, and then H equal Y sine alpha. So if you look at the problem, H average is given as 10 meters. So when we do this, here we have Y average.
Okay.
So I have to plug in, instead of Y average, I have to say 10 H divided by sine alpha, which is 60 degrees. Am I answering the question?
Yes, thank you.
All right, thank you, you're welcome. Okay, so, but this is exactly the way we develop the formulation. Well, let's do something more tricky. Okay, so I'm trying to follow a trick. Oh, before we go on, turns out, okay, so now I just want to plot here. This is the pool, this is the wall of the pool. This is the liquid. And then let's say this is how the pressure changes. It increases as it goes down and down. Okay. So if I put a valve here, and then I put the same valve here, the question, will the difference between the centroid, and then the center of pressure, will it change? And the answer is yes, because here there's more pressure, and so the differences between the upper and the lower portion here are less than here, because this is deeper. So what we did calculate, we calculated at the depth of 10 meters, and we ended up with a result of 0.08866 meter, 886 for the shift between the center of pressure and the centroid of the area. But if you go deeper, that distance will decrease. Okay, so this is just one example. So the deeper you go, the less the difference. The higher, of course, if it's going to be almost on the surface up here, then the distance could go maybe 40 centimeters, which is pretty large. Okay, that just to show this thing. Okay, so here is one that I can play tricks. Okay, and every book has something similar. So let's see how can we work this one out. So, okay, there's a gate. We know that the area, so the shape of that gate is 4 by 4. And it held by, let's say, 2 rivets or 2 screws, which are F1 and F2. We would like to find out what is that. Let's say you want to put a glass window on a pool. You're a civil engineer. You want to know how much force you need to hold those little brackets down or so. So we need to find out center of pressure location, and basically the force F1 and F2. But you cannot find F1 and F2 without finding the center of pressure. So there's no rocket science here. So let's see what we do know. We just look at that very quickly, and then let me get the pen before it jumps on me. So I can do the area. So I'm working like the student. So you just want to do first what is easy. So I'll do the easy stuff. So I can tell right away that the area is 16 meters square. I can also look and figure out what is the depth of the centroid, because the depth is 2 meters, so the length is here 2 meters. So that is going to be H average. H average. So what is H average? It's going to be this 1 meter, which is that one here, 1 meter, and then 2 meter cosine 30 degrees, which is this distance. It's actually cosine 120 degrees, but I wrote it cosine 30 is the same thing, okay? So then how much is Y average, okay? So what you can do is divide, you can say Y average is H average divided by cosine 120. Okay. So, but it's the same as cosine 30. So that's what I did here. Okay. And then plus 2. So where is the coordinate system? The coordinate system is this. And then we have Y going that way. And this is the Z coordinate. Okay, so it's a bit misleading. So for that point, the Y average is the distance from here to here. And this is what we calculated right here. Okay, so H average and Y average. Very, very simple.
Professor,
Yeah.
did you just choose those coordinates or are they like given?
No, I was saying that if we want to go by the model we developed earlier, then this is how the coordinates supposed to look like.
Okay.
Okay, so I'm trying to tell you that it could be shifted in different geometries. Okay, so that's what it is. And okay, so we good. So we get these distances. So now with the moment of inertia, with the average depth, we're going to be in good shape. So let's see. The average pressure, we know density, G, and then we know the average H, which is this one. We just calculated it right here just by looking at the problem. We were able to figure that one out. So that's the number, the average pressure at that point, which is at the centroid. So at that line, which is here, that's the average pressure. How much is the force? Average pressure times the area. We know the area, it's 4 by 4, 16. Okay, here we got the formula, we got some number, okay? I hope my calculator is good. Now I'm going to show you my calculator. I use the regular old-fashioned $12 calculator. Actually, it's $8 from Walmart. Okay, so it's very clear where the force is acting. The force is acting this way. This is the direction, but it's probably acting somewhere down here. So FZ is probably here. So we need to find out that point. Okay, what's the difference between these two? Okay, which is going to be YCP minus Y. Again, it is symmetric. Okay, we said it's a 4 by 4. It's symmetric, therefore, IXY is going to be equal to 0. Dynamics and statics, I'm quoting, it's not me, it's true. And okay, so let's see the formula. So we have only Y, the shift in Y down, in this case, moment of inertia. What is the moment of inertia? It's going to be the width times height to the third divided by 12. If you have second thoughts about it, here is that, if you see. This is the moment of inertia. Okay, so width, how wide it is, how high it to the third divided by 12. So this is where we were. Okay, so we take, that would be the moment of inertia. This is the moment of inertia. Y average, we just calculated Y average here, 3.1 Bergen. And then the area, we calculated at 16. The shift is almost half a meter, 4.423. And now, okay, so the force, okay, let's go back. So let's see, so, oh, I already have the plan. Okay, I have the plan. So we have a force, which this is the centroid. This is the force, Fz, Fz. And then this distance is 0.423. Okay, so what I can do is I can do moments about, what did I do moments about? I took moment about this axis here. Okay, so the moment about this to this direction, okay, it is going to be F2 times the distance, which is 4. F2 times 4, which is this 4. And then the moment to the other direction is going to be Fz times this distance. Fz, which we calculated right here, and times the distance, which is 2 plus this thing. So 2.423. Making one equal to the other, solving for F2, end up, this is the force F2. F1 and F2 are equal to Fz. Again, I'm quoting from statics. Therefore, this is Fx, of course, Fy, sorry, Fy, or Fz, sorry, Fz. And this was Fz as well. And therefore, that's the second force. Very, very simple. So you need to have a little bit of statics. That's why you have the prerequisites for that course from statics. Okay? So this was a bit trickier than the previous one. The reason is that we kind of try to play with the coordinate system. The coordinate system not completely clear. So you have to figure out that the coordinate system should be placed at that intersection with the liquid height and with the coordinate system, with the plate. And therefore your Y average is going to be this distance. It's going to be messy now. Okay, so that was the trick. Let's do another one, which I believe that's the most complicated. Okay, so I usually say, this is also in the book, this is the most complicated, and it has two elements. It has an asymmetric area, which we need to calculate the forces on. And so we're going to have a mixed moments of inertia. And it also, the origin is not at the pool itself, okay? So that's it. Okay, so we have a pool where the shape is shown here. Right? This is the shape. And then at the bottom, there is a 30-degree flat surface. And in that surface, there is a triangular plate. We can call it drain valve or whatever. And we would like to find out what is the force and what is the center of pressure in order to find out how to support it, what kind of forces to apply and all that. So the problem is given that the top tip, the apex of that triangle is located at 5 meter depth. Let me see, I have the pen, yes, I have it. So this is at 5 meter, which is here. And then the base of the triangle is located at 6 meter. Okay, so we kind of know where is that thing, okay? And then we know the shape, which is 8 meter by 6 meter. That's the shape of the triangle. This is a right angle here, okay? It's a right angle. And the shape is inclined by 30. So let me just go over very quickly about what are the messages. So first of all, we need to find the centroid of the triangle. Centroid for a triangle is 1/3, 2/3, if you remember. So it's going to be 1/3 towards the base in this case, and 2/3 towards the up. Same story goes that way, okay? So if it's 8 meter plus, if it's 12 meter long, oh, it doesn't say 12 meter. We figured it out ourselves. Okay, so what we have, no, it's given. It's given, it's 12 meter. So if it's 12 meter, then the centroid is going to be 4 meter, which is 1/3 of 12 from the base, okay? And then what we need to figure out is where is this point? How deep is this point? And that's going to be the centroid. So it's going to be 5 plus this thing sine 30, okay, the way it is shown. 8 meters sine 30. That's probably how deep it's going to be. And then we can calculate the forces. So it's going to be base times the height divided by 2. Very, very simple, okay? So, okay, so that's going to be easy. Then we need to figure out moments of inertia. And let me just go back for a second before we continue. So do you understand the problem, the geometry and all that?
No.
Yeah, okay. So if you understand the geometry and you try to think the way I'm trying to explain, is that, hey, I can figure out where is the centroid of the area. I can see where the y is. Why can I see it? Because the coordinate system is actually here at the intersection between the surface. And therefore, this would be y average or h average. This is h average. Or y average is going to be this distance here. My hands are not stable. This is y average, okay? So at least visually, you know what are we looking for. So let me just go back to that table we had before, this one. So we're gonna face that case. So assuming that we know the centroid, which is 1/3 of the height, okay? And it's on the bisector, but if you look at the based on the base, it's gonna be 1/3 and 2/3. The same story. Now, moment of inertia about this axis. Moment of inertia about this axis here, it is going to be base times the height to the 3rd divided by 36. The shift or the IXY is going to be B, which is the base, B minus 2 times the shift, okay? And then L squared. So instead of L third, it's L squared, but we have another B here. So if this triangle is going to be a right angle triangle going all the way to here, then in this case, B is equal to S. So then what is going to be here is going to be minus 2b. So it's going to be minus b here. So it's going to be minus b squared L squared over 72. Are you good with that? That's the trickiest part of the whole thing, okay? Which is simply statics or dynamics, okay? So let me go back to the problem. Okay, here we are. So we presented that one. There is a mixed moment of inertia. Let's try to solve it. Okay, so solution is gonna be pretty easy. So let's see, the centroid. How deep is the centroid? We have 5 meters. Let me get the pen before it jumps on me. We have 5 meters, the depth. Then we have this distance, which is 8 and sinus 30 degrees, right here. Turns out it's 9 meters. Okay, sine 30 is 1/2, so it's going to be 4 plus 5, it's 9 meters. Average pressure at that height or that depth, H average, okay? This is our H average. We call it centroid. Rho GH, that's it. That's the pressure at that point at the center of the triangle. What is the area of the triangle? Base times height divided by 2. We know that. What is the force? Area times average pressure. Average pressure we just calculated here. Average pressure, area we calculated here. And then minus, because the average force is going to act, actually is going to be below that. This is going to be Fz. Very simple, okay? Exactly the same thing. So what are the tricks in this particular case? You have to place the coordinate system here. Right now, the y-average is not important. This is the y-average, but the y-average will show up in the moment of inertia. So you have to be careful about that. Okay. All right, so let's go on. Let's go on. All right, so I just brought that page again. So IXX, I'm looking at the table. I just brought up the table. It's base, height, base is 6, height is 12. We'll pick up the pen. Here we go, base, height to the third, divide 36. Everyone can do that, no problem. Mixed moment of inertia. It's going to be B, which is 6, another B, which is 6. S, the shift is all the way to here. Therefore, our S is equal to B. Therefore, minus 2B, this ends up being minus 6 or minus B. You multiply and you end up with a minus sign. The minus sign in the shift means that, let's look at that picture, means that there's more area here and there's more pressure here because the pressure increases like that, linearly. So remember our x-coordinate kind of didn't get it right, but the x-coordinate goes this way. This is the x-coordinate, and relative to the center, so the x-coordinate would be here, we're going to shift the center of pressure by a minus quantity, not positive. And therefore, this minus quantity is going to be, the shift is this minus 72, the moment of inertia. The y-average, which I mentioned earlier, this distance, we need to calculate it now, right here, divide by some 30. And so it's going to be 18 meters. We need that here. It's a y-average. Need that here. This is coming from the moment of inertia, 36, and this is minus and 0.4. So this is actually exaggerated a little bit. This is, let's say this is that much, so actually it's more like here. Okay, so that's the solution. Okay, one more time, that was the most complicated problem, and still, if we follow the routine, it is going to be very, very easy and looks exactly like what we did before. Okay? Can I move on?
Professor, the formulas that you had for the triangle on the previous page, those formulas for IXX and IXY, they go for the right triangle and for that slanted one, right?
This is the IXY here, and here's the IXY.
But I mean, those formulas work for the triangles that are perfectly at 90 degrees and the triangles that are not perfectly at 90 degrees.
I mean, this equation is correct for anything. In our case, the triangle looks like this. Our triangle is this. Okay, and in our case, the shift is actually B. The same as this, as the base. Okay, but this formulation works for all triangles. The apex can go all the way. So if this is going to be, if S is going to be B half, which is a symmetric one, then that formula should be 0. So B minus 2 B half is going to be 0. Yeah, it works. You see? Okay?
Yeah. Okay.
All right. So it has to be with the moment of inertia. Okay, I move on. So in the book, I actually included a chapter for more complex shapes where you have to integrate the surface shape. But, okay, so here's a quick summary of what we did so far. I expect you to be able to solve problems like what we did now, okay? Now, if you have, we're not going to have curved surfaces, but this is for you guys, you're going to be engineers, and if you need to make a back of the envelope calculation, you can do it without really doing heavy going integrals. So the way to look at that, if you have a, say, a curved surface, then you're going to take just the, and I mentioned that at the beginning, you just take the reflection of that surface, find the centroid, multiply by the average pressure, and then you know what is the force on this surface. So that would be Fx or Fz, depends on what the coordinate system here. The force to this direction is actually even easier. You have to calculate the weight of the fluid above that surface, okay? So if this curve is given, and then you can calculate the area here, then you know what is the weight of the fluid in this area, and then in another straight areas, you just go with a straight line, so it's going to be a square. So you calculate the weight of the fluid. This is exactly like we had the bricks, you remember at the beginning? Same problem, and therefore the force on the floor, you can calculate by the force divided by the area at the base. So it's going to be the same thing. Okay, so this is just back of the envelope, so you'll know in the future how to calculate forces like that. There's another example. If I have something on the bottom of the pool, okay, there's a pool, and I want to find out how much is the force on that one, I can just simply take the weight of the water in that area, and that's going to be the force on that one. Okay, so the same example. Okay, so with that, I would like to conclude that discussion about forces because semester is short and we have to keep on going. Okay, so let me continue. So what's coming next? Let's see. We are still in the hydrostatic chapter. So we need to talk about buoyancy. Now, this section is going to be super easy because Mr. Archimedes figured that one out, well, let's say 2,000 years ago, okay, maybe a few years less. Okay, he figured that out, and it's not only figured it out, he made some statements which are extremely accurate. So one more time, we're looking at several cases. There's my pen. We're looking at the floating object. We're looking at the submerged object, and we're looking at something at the bottom of the ocean. And I already mentioned that the force on that guy is going to be equal to the weight of the water pushing on it. Okay, that's going to be the force. As long as we assume that it is glued to the ground, to the floor. If there's liquid underneath, then this is the formula that applies to that. So Mr. Archimedes, or we can call him Dr. Archimedes. I don't know if those days they gave doctors. Was he with Alexander the Great? Anybody who is a in history, just remind me of that. Anyway, I think it's the same time, same frame. Anyway, so he said that anything in the fluid, immersed in the fluid, will experience a buoyancy force, the lift force, which is equal to the weight of the displaced fluid. So that's how the ship floats. And then if it's inside the water, it still experiences, which is equal to weight of the water, which was, again, displaced. So the same thing. But in the first case, you may claim that the displaced fluid, the weight of the displaced fluid is equal to the weight of the vessel because they are in equilibrium. So If a ship sinks so much in the water, then the displaced water weight is equal to the weight of the ship. Very interesting. Archimedes figured that one out. And then he said something else, which is kind of fascinating. He said that the buoyancy force acts at the centroid of the area, which is the displaced fluid area. And I'm fascinated by the third one. He must have been a pretty brilliant gentleman. And he lived way back there. And it just shows that we are not so smart. Some of the people were pretty smart over there. He must have had a cell phone, but didn't stay so long. Anyway, let's try to prove those observations and do a few examples. Again, this is just to close this chapter about hydrostatics, and we have to pay attention to that. You guys studied that in high school, if you did go to high school. And so I try to prove the first and second observation of Archimedes, and there are two ways. There's a simple way and there's a more complex way. The simple way is this. Okay, so we have I put a rectangle shape, which is very simple. So it's a cube, okay? It's rectangular. It has an area S, and again, the same area is at the bottom. This is the same area. And then the force pushing it down, which I call it F1. Okay, I have to write it then. F1 is rho GH1, which is the pressure, times the area, which is S. Okay? We can look at the bottom, and there is a force acting on the centroid of the lower surface, F2. No rocket science here. It's going to be rho GH2 times S. Obviously, the F2 is larger because it's deeper. So what is the difference between the upper and the lower surface? Right here. You want to call it lift is the difference between the force on the lower surface versus the upper surface. Rho G, we take the H2 multiplied by the S. Turns out the volume is these things, the difference between the two height, that's the height. Area, that's the volume of the object, of the cube in this particular case. Therefore, what happened to my pen? Therefore, clearly, the lifting force is equal to the weight of the displaced liquid. Okay, very, very simple. I have a few minutes left, so let's do the hard way. And I'm going to call those that got an A in calculus. People with the A in calculus, please remind me of Gauss' theorem. You learned about Gauss' theorem, who said that you can convert a surface integral to a volume integral. Anybody brave enough to tell me that he remembers that? I just want to hear a voice. Nobody brave enough?
I am here, but I only got a B+ in calculus as well.
It doesn't matter, but you remember. So, you know, your grades were not so great, but your memory is excellent. On the long run, you're ahead of the curve, okay?
Yeah.
That's very good. That's very good. Okay, thank you very much. So that's the integral. So now, let's see. So what we have is basically, we have a surface, and it has a volume, and we would like to integrate the forces, rho GH force, okay, around this object, okay? So what we need to do is we really need to take the pressure, the local normal, which is going to change, and integrate it ds all over the place. But Mr. Gauss told us that, forget about it. You can just take the gradient of P and integrate it over the volume. So you can actually get some slices with the volume. Do I have the pen? I don't want to lose it. Okay, you can just say, take slices and just get the P and then figure out what's the area. Now, we can actually get smart about it and we say, well, what is the pressure? Rho g minus z. And then just take the derivative, dp dz is minus rho g. Gradient here is a 3-term in the Cartesian coordinate system. So the gradient p in our model here is going to be 0, 0, and minus g. So let's play with the integral. So let's, instead of force, we're going to say lift. It's going to be equal to this integral, because this one we know, this is what we said before, but it's complicated. So instead, we're going to do this integral. So it's going to be integral of volume, gradient p, and dv. But turns out that the gradient is a constant. So we put the constant in front. Integral dv over v is going to be simply the volume. So lift.
Same. I'm just. This class is
Rho
too fucking long.
gv. What was that guy saying over there? Okay, so it's the same result. Same result. We almost finished. And so it's good to remember algebra or calculus, but jump simple results as an engineering work as well. Okay. At that point, I would like to conclude the discussion. Any questions for today? You very quiet. How many of you I still have? Some of you running away. I have about 110 of you or so running away.
We're physically here.
Some of the brave people are still here.
I'm still watching.
Thank you, Professor.
Yeah.
I have a question.
Go ahead. Louder.
It's more about the format of the exam. Whenever we have the exam, how is the format going to be? Is it going to be like a question or a couple questions from each chapter, or we send pictures in? Like, how are we turning this in via online?
The exam?
Yeah.
Okay, luckily I had half a semester last semester. So what I did is I posted on Blackboard the exam exactly at the time. And then you had an hour or hour and a half, whatever, to do the exam, and you send it to me, and you have to raise your right hand that you're not going to have grandma helping you. Okay, something like that.
Sounds good. Thank you.
And it worked. I mean, you're trying to show what you know, not what other people know. I mean, this is supposed to be the honor system.
Mm-hmm.
Again, we are in a different time now with the pandemic, and this is what we're trying to do. And I mean, I can send the police to you, and then I'm going to need a huge police force with 150 students. It's not practical.
Thank you.
Okay.
Thank you, Professor. I appreciate it.
Okay. All right.
Professor, you said if we attend all of the lectures, we get automatic A's on the exams, right?
I said 10% at the end.
Oh, okay. I misunderstood.
10%? 10%?
Only those that wash my car every week.
Right over.
So it's more difficult to get an A. Okay, ladies, gentlemen, thank you very much. I don't know. Again, I have no feedback. I don't see you at all.
Goodbye, sir.
You know,